Welcome to The Explainer. Today, we're taking a seriously mind-bending geological road trip. We're going to trace the longest active continental margin in our planet's entire history. So buckle up, because we're traveling back hundreds of millions of years to a world that would look totally alien to us today, a world completely governed by just unimaginable tectonic forces.
Let's kick things off with a pretty staggering number, 18,000. That's the length, in kilometers, of the ancient Terra Australis origin. It was this awe-inspiring, massive mountain belt that honestly dwarfs absolutely anything we have on Earth right now. I mean, to even wrap our heads around how a mountain range of this size existed, we first got to reconstruct the massive supercontinent it sat on.
Here's our roadmap for the trip. We'll start with the longest edge on Earth, figure out what exactly West Gondwana is, and look at the Supercontinent Assembly line. Then, we'll dive into South America's tectonic puzzle, see how Africa and Antarctica linked up, and wrap up with the Earth's moving margins. Let's get into it.
Section 1. The longest edge on Earth.
Looking at the big picture, you really start to grasp the sheer, mind-boggling scale of the Gondwana margin. We're talking about an active oceanic edge stretching an incredible 40,000 kilometers in total. And right along the Paleo-Pacific and Iapetus zones, yeah, it's along that massive perimeter that our 18,000-kilometer Terra Australis origin sat. The absolute length and the intensity of this ancient active margin makes today's Andes Mountains look, well, kind of like speed bumps.
Section 2. What is West Gondwana?
You know, our earliest geologically based understanding of this whole divide actually dates all the way back to 1937, thanks to the pioneering work of Alexander Dutoué. By conceptually slicing the supercontinent in half, he linked South America, Africa, Arabia, and West Antarctica. At the time, this was a totally revolutionary way of seeing how our modern continents were basically just puzzle pieces of a much, much larger whole.
Now, to understand how that specific West Gondwana puzzle actually came together, we got to talk about cratons. What are they? Well, they're the ancient, incredibly stable cores of the Earth's lithosphere. Think of them as the unbreakable foundational building blocks of the planet. They've somehow survived the crazy, violent cycles of merging and rifting that ultimately formed the continents we know today.
Section 3. The Supercontinent Assembly Line.
So, this assembly line actually kicks off with the violent destruction of something else entirely. Between roughly 1,000 and 750 million years ago, an even older supercontinent called Rodinia broke apart. And this breakup essentially triggered a massive, chaotic series of oceanic closures and tectonic collisions starting around 850 million years ago. It took literally hundreds of millions of years of rock relentlessly smashing into rock to finally glue Gondwana together into its fully assembled state around 490 million years ago.
Those individual indestructible puzzle pieces we just talked about, specifically the Amazonia, Congo, Kalahari, and Rio de la Plata cratons, they were the main characters here. During this huge assembly phase, these blocks just smashed together, squeezing out and closing up entire ancient oceans. The complex, folded geological lines left behind literally mark the violent, ancient suturing events that welded them together forever.
Section 4. South America's Tectonic Puzzle.
Moving on to South America, we run into what geologists call terrains. Think of them as geological hitchhikers. A terrain is basically this alien fragment of crust that rides along on a tectonic plate, crashes into a larger continent, and just permanently attaches itself to the shoreline. And the wild thing is, when they arrive, they bring their own completely unique, distinct geological history with them. It's kind of like a traveler showing up at customs with a passport full of exotic, faraway stamps.
And right at the Guyana terrain, also known as the Precordillera, we hit a massive scientific mystery. This specific block of rock features a sequence of Cambrian to Ordovician limestones that harbors an incredible secret. The ancient brachiopod and trilobite fossils trapped inside it, they look exactly like the ones found in North America. They are completely out of place in South America.
As you can imagine, this little anomaly has sparked a fierce, ongoing debate in the scientific community. On one hand, you have the Laurentian origin camp. They argue that this terrain literally broke off of ancient North America, drifted all the way across the deep ocean, and slammed into Gondwana. On the other hand, the West Gondwana origin camp proposes it was actually always part of this supercontinent and merely slid into its current spot along a massive strike-slip fault. Both sides fiercely wield uranium-lead zircon dating to back up their claims, making this one of the absolute most tantalizing open mysteries in South American geology today.
Section 5. Africa and Antarctica linked.
Okay, so if you're looking at a modern globe,
This next part is going to seem completely counterintuitive. Seriously, how does a folded mountain belt in modern-day Argentina seamlessly connect to landmasses that are now separated by thousands of miles of the deep Atlantic Ocean?
Well, geologists solved this puzzle by realizing these pieces used to be next-door neighbors. The rocks of the Sierra de la Ventana in Argentina, the Cape Fold Belt in South Africa, and the Ellsworth Mountains in West Antarctica were all originally part of one continuous, shared deep-time basin. Historically, this was called the Samfrau geosyncline, a massive passive margin. Over millions and millions of years, it quietly just accumulated miles of sediment. That is, right up until it was violently folded and thrusted upward during the massive Gondwana orogeny.
Section 6. The Earth's moving margins.
The edge of the world didn't just stop evolving once it came together, though. It transformed dramatically over time. First, the final terrains crashed into the coastline, effectively sealing the margin. But then, the whole system just totally switched gears. During the Permo-Triassic period, the margin experienced massive extensional tectonics. The crust literally stretched and thinned out, which triggered this voluminous phase of volcanic eruptions and the pooling of enormous granite batholiths deep underground. Ultimately, all this intense stretching and recycling set the exact stage for the modern Andean subduction zones we recognize today.
So why does all this deep-time geology actually matter to us? Well, the crucial takeaway is that this dense tectonic history isn't just abstract science. The ground beneath your feet right now, whether you're in South America, Africa, or even New Zealand, is a heavily recycled relic. It's the mashed up, melted, and reformed product of an 18,000-kilometer mountain range that was built and then totally destroyed over hundreds of millions of years.
Which leaves us with one pretty awe-inspiring thought to close on. If geological forces were powerful enough to build a 40,000-kilometer supercontinent margin, raise the longest mountain belt in planetary history, and then completely rip it all apart to form our modern oceans, well, those exact same unstoppable forces are still churning beneath our feet right now. So, what will the map of the Earth look like 100 million years from today? Thanks for hanging out with me on this deep time journey here on The Explainer. Until next time, keep looking down and keep wondering.